1 second. All right. So, welcome back to Math 161, everyone. We're going to dive headfirst back into things using synthetic division in a second, but I just want to point out a couple of other details. We're only going to do 3 regular tests in this class. I typically do 4, but we only have time for 3 because we lost the week after spring break due to planning. And then I think I lost another 1 or 2 days, at least one more because of the power outage, internet outage last week. I feel like there was another that I lost, and those are pretty significant hits for a 12-week class. Hold on. So again, those are pretty significant hits for a 12-week class, especially considering the new format. In terms of pacing, I feel like I'm keeping it about the same as in class would be, but probably, I don't know, maybe 5 or 10% slower. Plus having to do these little rants. So test 3, this is what I'm thinking for test 3. We're going to start it on Thursday, the 30th, and end it Monday or Tuesday. This may be Monday, 5/4. Or Tuesday the 5th. I'm not sure. I think I'd rather do it Monday because most likely our final exam is going to be on the 7th. There is not going to be a date range for completion of the final exam. You need to understand this. The final exam, you will have 24 hours to do, and that will be it. So it's going to be a tighter test. It's going to be all-inclusive. It's going to cover everything from the beginning till whatever we finish. Sorry about that. And again, I have a question mark there. I'm pretty sure it's going to be the 7th, but I just want to make sure before I say that definitively. And then test 3, like I said, will cover chapter 3. We're still going to talk about some stuff in chapter 4. I'm just not going to have an individual test based on it. It will be just discussions, homework problems. Sorry, I'm coughing really bad today. I've had to turn my mic off a lot so I don't kill your ears. So if that's why you keep hearing me clicking, that's why. All right, so let's get back into the material. Yes, of course. Tests are timed. I'm sorry. Tests have to be timed. You can't really do anything about that. Someone asked. So synthetic division. We did a whole boatload of these problems last time. Did we finish all of them? Yes, we did finish all the synthetic divisions. And we said this was a much quicker way of doing division versus the standard long division. Now, I will admit, you can just always do long division if you really, really, really want to, but but the problem is you're going to waste an insane amount of time in this class because the problems that we are going to need this division for can always be done synthetically, and you may have to do 2 or 3 or 5 or 10 or 15 of these just to even begin a problem. So this synthetic division stuff, it is very, very important. It is going to be used a lot more moving forward. So you wrote a little number in a half box. So let's say we had some function and we were dividing by x minus 3. That means you put 3 in this half box. Now, if the top was, say, 1x squared plus 3x minus 5, then to the right of that would go the 1, the 3, and the minus 5. You draw a line and a plus sign. Remember, this 3 has changed signs from what you see in the bottom originally. You bring the first number down, you multiply and then add, and then multiply and then add. 1 times 3 is 3. Add, you get 6. 6 times 3 is 18. Negative 5 and 18 make 13. From right to left, that goes your remainder, your constant, your coefficient of x, your coefficient of x squared, et cetera, et cetera, et cetera. So that says that the answer would be 1x plus 6 plus 13 over x minus 3. That was the whole process. And again, you have to have that down. So what we're going to get into today is actually how we use this for problems that don't just say do the division, for problems that have a more important meaning to them. And we're going to start this with the remainder theorem. And this is something we really honestly won't use again in this class, except for one idea, and that is if the remainder is 0. The remainder theorem says, if a polynomial, if a function f of x, that's a polynomial, is divided by x minus c, and again, I'm reminding you that you should use synthetic division. Long division works, but this is the better way. Whatever the remainder is f of c. So in other words, we're saying that if you were to plug in c, the number that you're dividing x minus by, let me say that more specifically, that was said poorly. When you divide by x minus c, the number, the minus c, so in this case the 3, if you were to plug this 3 into the function, the remainder theorem states that the answer to plugging 3 into the top function is the remainder, and that's 13. This is helpful to make difficult evaluations of higher order polynomials. I don't do a lot of proofs in this course. I love this proof though. I think it's important to see. So if a polynomial f of x, so we are given, we have some f of x. Let's take it. Excuse me. Let's divide it by x minus c and see what we get. So we have f of x, and we're dividing by x minus c. Well, what do we get is the quotient plus the remainder over the original divisor. We said whenever you do this division, you get a quotient, which I'll write as q of x, plus the remainder. Now this is generally a number, but I'll write it as a function. And then divided by the original denominator. Well, the original denominator is x minus c. Well, let's multiply. We're going to do, again, proofs. We just do steps to do steps. Let's multiply both sides by the denominator, x minus c. Why are we doing this? We're clearing denominators. We like to clear denominators in math very, very often when we have equations. So we'll take x minus c times the left side, x minus c times the q, and then x minus c times the third fraction. So that's f of x over x minus c equals, and times the quotient, plus times the remainder over the x minus c. Oops, one too many c's. We do this because x minus c's top and bottom cancel. Now it doesn't happen with the quotient because it wasn't a fraction, but it happens with the remainder term as well. So what this tells us, and this is important, that a function can be rewritten as x minus c, that thing we divided by, times the quotient if we actually did the division, plus the remainder. Now I'm going to drop the function dependency on the remainder. Again, I'm not saying that this of x part just disappears. I'm just dropping it. It literally means the same thing. We've emphasized this in this course. I'm not technically changing anything here. So now, to prove the remainder theorem, plug in c. So that f of, and I'll show it in color, c equals, this will be x minus that c times the quotient, and we'll plug in c to the quotient, and then plus the remainder. X, I'm sorry, not x minus c, I wrote that wrong, oh Lord. We are plugging in c, we're plugging in c here, that c was already there. So it goes, parentheses, c minus c. Again, the red is what's been plugged in, times the quotient, everything else was right. Sorry about that. Plus the remainder. Well, guess what? C minus z, c minus c is 0. So this is 0 times whatever the quotient is with that c plugged in, which again, I don't even know what the quotient is. I don't see it. We didn't evaluate it. And the reason we didn't is because 0 times anything is 0. So this whole thing is the remainder, which means f of c is equal to the remainder. And that's the remainder theorem. So there's the proof. I will never ask you to reproduce this. It's honestly nothing crazy. All I did is clear fractions and plug in a number. That's all I did. But it gives us a very important concept that if you have some function, and maybe you want to know what f of 2 is, or f of -7 is, or f of 100,000 is, or f of 1.3 is, sure, you can just plug those numbers into the given function. And if your function's pretty ordinary, that's exactly what we would want everyone to do. But let's say your function is like x to the 5th minus 7x to the 4th plus 43x to the 3rd minus 17x plus 9. You gotta do all sorts of exponential evaluations, multiply by coefficients, add and subtract like terms. It's a whole ordeal, especially without a calculator. Now, this is a calculator allowed section, but not for every teacher. So if you had to do those things without calculators, it can be a real giant pain in the butt. But this synthetic division process, it's just multiply adding a bunch of numbers. It never really gets too complicated. So if you can do this and knock it out in 30 seconds, as opposed to maybe 5 minutes of exponential evaluations in PEMDAS, the remainder is the answer that you would have gotten the other way. That's what this says. So let's try that out. And we will show that this actually works, because I'm sure a lot of you don't trust me for the moment. It seems weird. And we stopped at example 3. And we're just gonna do 2 of these. So evaluate using the remainder theorem. So for A, we'll have f of x is equal to x cubed minus 7x squared plus 5x minus 6. And we want to find f of 3. So again, before today, I expect every single one of you to have been able to do this problem. You just plug a 3 here, 3 cubed minus 7 times 3 squared plus 5 times 3 minus 6. And you get what you get. But now let's try this with a different approach. Now again, the point of this class is not to say to use this particular method. It's to have lots of different ways to do things, have options. So that's why I want to explore this remainder theorem. So what we're doing is we're saying we will divide f of x by x minus 3. That's what we're doing. We're taking f of x and dividing it by x minus 3. Why a minus 3? Because we're plugging in a positive 3. This is the number that would go in the half box. So we have to change the sign for the division. So that's x cubed minus 7x squared plus 5x minus 6 over x minus 3. And you could do this with long division, but we're going to use synthetic division because it's quicker. That says 3 goes in the half box. The number being evaluated is the same sign as what goes in the half box. These are the same. You're changing the sign when you're putting that number in the bottom, the x minus the number. To the right go the coefficients, which all are listed and in descending order: 1, minus 7, 5, and minus 6. Leave a blank space. Plus sign, and then the process. Bring the 1 down. 1 times 3 is 3. Negative 7 plus 3 is negative 4. Negative 4 times 3 is negative 12. 5 minus 12 is negative 7. Negative 7 times 3 is negative 21. Negative 6 minus 21 is negative 27. That's all we have to do. Now, I did not ask you to show what this thing becomes. Yes, it would end up being x squared minus 4x minus 7, then a minus 27 over x minus 3, but that wasn't the point of the problem. This wasn't to simplify some division. It was to evaluate a function. This right here is the remainder. This is the answer. F of 3. The remainder we got when we plugged a 3 into the synthetic division was negative 27. So the answer is negative 27. Now, if you don't trust that, just for the sake of time, there we go. We're doing f of 3, so this was 3 to the third power minus 7 times 3 squared plus 5 times 3 minus 6. So if this theorem is true, just directly plugging 3 into the function should spit out negative 27. Drum roll. Negative 27. It works. But Mr. Beckner, I could plug that in way quicker with my calculator. Okay, yes, but again, the point is options. The point is maybe you don't always have a calculator in front of you. Maybe you're not allowed to have a calculator, depending on the situation. I went through most of my college degree, program without ever being allowed to touch calculators. So this doesn't involve squaring or cubing numbers, this synthetic division. It's just multiplying, add, 2 very simple steps. And what if these exponents were worse? What if these were exponents of 5, 6, and 7, and we were plugging in f of 17, some ungodly number? Those would be ridiculous to have to crunch the exponents with. We get ridiculously big numbers that we have to then add and subtract. It's just a bigger pain in the butt. Wow, that looks weird. So, B. I think I can squeeze that in here. Let's do f of x equals x to the 4th plus 5x to the 3rd plus 5x squared minus 5x minus 6. And we want to find f of negative 2. So because we want to find f of negative 2, we're going to do synthetic division, where we take f of x and divide it by x plus 2. Remember, synthetic division, you change the sign between the number you're evaluating and what goes in the bottom. 3a, the answer was 27. What did you say the answer and was not the answer for example 3? I think you asked I'm not sure what you meant there. What did you say was the answer and was not the answer for example 3? The answer was negative 27. I hope I'm answering your question. If not, let me know. Okay, so again, going back to this function, we're doing f of negative 2, so that's why we divide by x plus 2. These sign changes are important, but the negative 2 is what will go in the half box. To the right go its coefficients, all are accounted for, and the powers are in descending order, so it goes 1, 5, 5, negative 5, negative 6, blank space with a plus sign. And an evaluation for simplification. Oh, okay, so that question, or what I said for a quote simplification, was if I just straight up at the beginning of the problem asked you to do this thing, if I asked you to do this, that answer would have been the quotient, which has the x squared minus 4x minus 7, then the minus 27 over x minus 3. So that would have been more like the examples we did last class. All right. My voice, hold on, let me cough. Probably shouldn't have my windows open at home. All right, so we bring the 1 down, and then it's just multiply, add, multiply, add. 1 times negative 2 is negative 2. 5 minus 2 is 3. 3 times negative 2 is negative 6. 5 minus 6 is negative 1. Negative 1 times negative 2 is positive 2. Negative 5 plus 2 is negative 3. Negative 3 times negative 2 is positive 6. Negative 6 plus 6 is 0. That is our remainder. That is the answer. So f of negative 2 is equal to 0. This is what we want moving forward. We like remainders that are 0. Why do we like remainders that are 0? Remainders that are 0 means that the division divides perfectly. It means that something was factorable, and we actually kind of already talked about that idea, that if the remainder is 0, that means you could probably, depending on your skill level, depending on the complexity of the problem, go back, factor the top, cancel it with the bottom, and then you just have a quotient as your answer with no remainder and no denominators left over. This is going to be the driving force of the rest of this section. When we try to do one of these evaluations and get a 0 remainder, this is an ideal situation. What this is going to allow us to do is to factor things that we may not have known how to factor previously. Because we have a very small amount of factoring techniques, all things considered. We have our difference of squares, sum and difference of cubes. We have our shortcut method. We have our trial and error method, our AC method, our box method, factor by grouping. But we don't really have techniques for 4-term polynomials besides factor by grouping. And honestly, in the real world, not a lot of problems factor by grouping. We have no techniques for 5-term polynomials or higher. And there are things that are 3-term polynomials that we would call prime, but we can still ultimately write them in a factored form. By using this idea of synthetic division, plugging in a number, getting a 0 remainder, it can give us factors. All right, so that is the factor theorem. The factor theorem is, in my opinion, the most critical piece of knowledge in this whole chapter. For some function, if you plug in a number, c, so c is a constant, a number, if you plug in a number and it spits out 0, that means x minus c is a factor. Think about it this way. When we ended up having some polynomial like x, oh, I can't write up there. If we had something like x squared minus 7x plus 6 equals 0, you factor it, you get x minus 1 times x minus 6. And then you set each of those equal to 0, which tells us x equals 1 and x equals 6. So when we're able to factor, we can get zeros that way. But what if you can't factor? Well, you have to use this alternative approach involving this factor theorem. It says if you can figure out the zeros, you can work your way backwards to get the factors. So like if I know that x equals 1 is a 0, because in the process of taking a factor and solving it, you add or subtract the opposite of what you see, that sign changes. So if x equals 1 is a 0, then x minus 1, ooh, that is god-awful looking, is a factor. If x equals 1 is a 0, you can actually go backwards if you know that and say that x minus 1 is a factor. That's all this really says. For a function, if you if you plug in a number and it spits out 0, talking is hard, then that means x minus that number is a factor. So just change the sign. So in other words, if 2 is a 0, x minus 2 is a factor. If negative 2 is a 0, x plus 2 is a factor. It's a two-way street. Now, do you have to actually plug that number into the function, evaluate it, and get 0? No, you can do synthetic division. And for higher order polynomials, things like with x to the 4th and x to the 5th, they would be more of a pain to plug in over and over and over. It's a lot better to do this with synthetic division. So this idea can be used to factor a polynomial given one of its zeros and then find more solutions. Let me scroll back up for a second. Where was it? Where was it? There's a really loud vehicle in the air, letting that pass. I'm sure you could hear that on my mic. It'd be funny if you can't. All right, so going back up here to where we said that some function is x minus c times its quotient. Instead of actually plugging in the c and seeing that the whole thing is equal to the remainder, if the remainder is 0, so hold on, it was really distracting. Let me circle what I'm referencing. Let's go back to this, that some function can be rewritten ultimately as x minus c times a quotient plus the remainder. So let's take that thing, and let's just say that the remainder is 0. So again, that was x minus c times the quotient plus the remainder. So f of x equals x minus c times the quotient. I don't really need the variable dependency, but I'll put it plus the remainder. If the remainder is 0, then f of x is just equal to x minus c times a quotient, which is a factored form. And there's your factor. So c is a 0. If r is 0, because f of c is equal to 0, that means that the function is just x minus c, x minus that 0, the opposite sign, times the quotient. So let's use this idea and black example, what are we up to? 4. Before we get into the next section. Let's have the function f of x is equal to 2x cubed minus 3x squared minus 11x plus 6. Now let's say, given that x equals 3, my favorite number today, is a 0. So I'm telling you x equals 3 is a 0. If you plug in 3, it will make the function 0. I'm telling you that up front. So given that we know that, I want us to factor this, and I want us to solve it. Factor completely and find all zeros. So if you, before today, looked at this function, 2x cubed minus 3x squared minus 11x plus 6, if I just say factor and solve, you'd say, oh, well, it's got 4 terms, so let me try factor by grouping. Well, guess what? The GCF is x squared for this pair. There's no GCF for this pair besides 1. The parentheses won't match. You can't factor by grouping, and you're stuck in a lake without a paddle. I don't know of any traditional factoring method that will factor this. We have to use these new and, in quote, exciting methods, where if you know one of them, you can refactor this. So we know that x equals 3 is a 0. So if x equals 3 is a 0, then x minus 3 is a factor. i.e., in other words, the function can be rewritten as x minus 3 times some quotient. I don't have room to write the variable dependency. Again, it doesn't technically matter. It just says that our function is x minus 3 times a quotient. But we don't know what the quotient is. Well, we can find it by dividing by x minus 3. So we need to find q. Do the division. So we're going to take f of x and divide it by x minus 3. We divide by the factor. We're dividing out the factor to see what it would end up being. So this is 2x cubed minus 3x squared minus 11x plus 6, all divided by x minus 3. So we'll set up our synthetic division. 3, to the right go the coefficients, the powers are in descending order, and all are accounted for. So 2 minus 3 minus 11 plus 6, big space, plus sign. Bring the 2 down. 2 times 3 is 6. Remember, it's bring the first down, then multiply and add till the cows come home. Negative 3 plus 6 is positive 3. 3 times 3 is 9. Negative 11 plus 9 is negative 2. Negative 2 times 3 is negative 6. I don't know why I wrote that plus sign there. This was not really necessary. And then 6 minus 6 is 0. It wasn't wrong, though. Guess what? This confirms that 3 is a 0, because the remainder is supposed to be the output when you do the synthetic division with x minus c. So yes, in fact, f of 3 on this function is 0. If you did 3 cubed, that would be 27, times 2 is 54, minus 3 squared is 9, times 3 is 27, 54 minus 27 is 27, minus 11 times 3 is 33, so that's negative 6, plus 6 is 0. But what we needed out of this was the quotient. This piece right here gives us the quotient. From right to left, that's the constant, the coefficient of the x, and the coefficient of x squared. So q is equal to 2x squared plus 3x minus 2. That's the quotient. Therefore, finally, we can rewrite our function, f of x, as the factor, x minus 3. This is this. Times the quotient, which was 2x squared plus 3x minus 2. We just factored something that, quite honestly, via traditional methods, I have no idea how to factor. I'm not saying there's not a factoring method out there that doesn't work for it. I just don't know it, because this is what I would do. Because there's so many different factoring methods, you learn to pick and choose what's better and what's worse at times. But we're not done. The point of this was to find all zeros, to factor it completely. This is not factored completely. This quotient is quadratic, so we should hopefully be able to factor it. So, well, let's focus on that. The 2x squared plus 3x minus 2. Now we got a factor. And if it doesn't factor, then we'd have to do the quadratic formula on it. Well, there's not a lot of options for the a and the c, so I'd do AC method personally, but I'm sorry, I'd do trial and error method personally, but AC method would be fine as well. So factor pairs of 2, it's only 2 and 1, so that's got to be a 2x here and an x here. Factor pairs of 2 or 1 and 2, it's just a matter of which one goes where. We know that we need the sum or difference to be 3, so we need a product to make 4 and a difference to make 3. Well, we should probably put the 2 here then, so that the 2 and the 2 are multiplying to get us that 4, and then a 1 here, because then the difference of that 4 and this 1 would be 3. We've got to make sure the difference comes out positive, which means the larger product needs to be positive. The 2x times the 2 gives us the 4, so that has to be positive, and that makes the minus 1. This is completely factored. Once again, we have now factored a polynomial with a non-traditional method in a way we couldn't have done before today. But that's not all we want to do. We got to find the zeros, so we set the function equal to 0. Use our zero product rule, setting each of them equal to 0. So that tells us x minus 3 is equal to 0, which we already knew. 2x minus 1 equals 0, and x plus 2 equals 0. Add 3 to both sides. Add 1 to both sides. Subtract 2 to both sides. You get x equals 3, 2x equals 1, and x equals negative 2. The first and the third are done. For the middle one, you got to divide both sides by 2. And that tells us that x equals a half. there are the three solutions to this polynomial, the three zeros, the three roots, the three x-intercepts, lots of names. Now, there's something that we've just relied heavily on. I told you up front. Hold on, someone asked. For the homework, do you leave a half as a fraction? Yeah, most likely. We usually prefer fractions to decimals in my math lab, but just read the instructions. If they want a decimal, they'll tell you they want a decimal. So going back to the beginning of the problem, we wanted to factor and find all zeros of this function, but we were told this, given that x equals 3 is a 0. Do you think in the real world, I'm going to tell you that? Do you think in the real world your boss is going to tell you that? Do you think in the real world the evidence is going to tell you that? No, you got to figure that out. So how do you figure that out? Do you just go randomly plugging numbers in? All right, let's try 3, let's try 17, let's try a half, let's try negative 3.9. I mean, that's one way of doing things, but you're going to take a very long way of doing it. What we're going to learn in the next section is a technique that will give us a list of possible zeros. So we're going to start with maybe 10 or 20 options and whittle them down to 1 or 2 good ones that actually work, or 3 or 4, depending on the nature of the problem. So again, this is not a very typical problem. In the real world, you generally don't know this. You just have the function and they say factor and find the zeros. So how do we know to do the synthetic division with 3 to get the quotient? And this is why we really emphasize the synthetic division for function evaluation now, because if you just plug the 3 in, yeah, it shows that it's 0, but it doesn't give you the quotient, which is needed to factor. So don't think you can just skip the synthetic division. You have to do it, otherwise, how are you getting your quotient? So that will end 3.3, and it will segue immediately into 3.4. Finding the zeros of a polynomial function, the most broad way of finding zeros. Absolutely, there will be cases where the C is negative, and we will see that. Don't you worry. So if the C is negative, that means in the division, it's an X plus. You still have a negative number in the box, so we have to make sure we have organized where the sign changes and where it doesn't. Okay. So for any polynomial of the form C board, I'll just write it above. So this is the board. F of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus yada, 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 a sub 2x squared plus a sub 1 times x to the first plus a sub 0 times x to the 0th, which we don't need to write because anything to the 0 is 1. The same standard form of a polynomial we've written a couple of times together. All possible rational zeros. I did not say all zeros. I said all possible zeros. I also did not say just all possible zeros. I said all possible rational zeros. This does not include zeros that would have square roots or imaginary numbers in them. So this only gets us one of the 3 types of solutions. Does that mean it only gets a third of solutions? No, it just only gives us one of the 3 types. The most likely types, in fact, but we'll still see the other types as well. So PRZ is what I like to abbreviate this as. The prize. Keep your eye on the prize. So for any polynomial, all possible rational zeros are the plus or minus. So we have to account for positives and negatives. It could be either. We're not really sure which. So it could be positive 1, it could be negative 1, it could be positive 2, it could be negative 2. If we write a number, we account for both positives and negatives. So it's plus or minus the ratio of the factors of the constant over the factors of the leading coefficient. So I'm going to give a couple letters. This is pretty standard that we call P the list of the factors of the constant. So remember the number at the end. This is our constant, which we will relate to P, and the leading coefficient is the first number when they're in descending order, and that's what will relate to the Q. The upper and lower case doesn't matter. This is not Q for quotient, it's just the letter Q. So you're going to have to go to the side and list all the factors of these numbers. For instance, if this number was a 6, I would have 1 times 6, 2 times 3. Those would be the factors. So 1, 2, 3, and 6 would be the values of Q. If the constant at the end was, say, a 12, 1, 2, 3, 4, 6, and 12, I was making sure I had all those in my head. 1, 2, 3, 4, 6, and 12 would be the factors of the constant, so those would make up the values of P. So all possible zeros are every single number that divides into the constant divided by every single number that divides into the leading coefficient, but it could be positive or negative. You have to account for both. This can be a very large list of numbers depending on the problem. These are the numbers that you will then go and do synthetic division with and hope that you eventually get a remainder of 0. It's a hope and a prayer. There's honestly not a guarantee that you get one in the real world. In our problems, of course, one of them will be 0. It may be the first time you try, it may be the 5th time you try, it may be this 18th time you try. And quite honestly, even when you practice this 100 times, most of the numbers you're not just going to be able to look at and go, I know you work, or nah, I know you don't work. Some you can. Most of the time, it's really difficult. There are ways using technology to give us shortcuts, and I will, of course, show you that. But for now, let's just wax poetic and talk about how we'll find this. Use the rational zero test, which is this. This is the rational zero test, RZT, RZT, I can spell, I can abbreviate. Use the rational zero test to find all possible rational zeros. These are the possibles. Then what you'll do is you'll use synthetic division to find one that actually works. So these possible rational zeros will be your C's. So let's, for example, say you had just 1 and 2. That's all it was, just a 1 and a 2, which means you have to account for plus or minus 1 and plus or minus 2. You have 4 options. So my suggested method is you start with the smallest number in absolute and work your way up. So use 1, then -1, 2, the -2, 5, the -5, 12, the -12. That's usually a good method. Once you find one that spits out a remainder of 0, so you may have a couple of stalls. Maybe 1 doesn't work, maybe -1 doesn't work, maybe 2 works. So you might do some synthetic division that dead ends you. Welcome to the real world. Once you find the ones that work, you can actually factor it like we did in that example, the last example of last section, as x minus the number that actually worked times whatever you get for the quotient based on the synthetic division. So once again, you don't just plug these numbers into the function looking for a 0 output. You need to use synthetic division, because otherwise, how are you going to get that quotient? You might say, oh, we use long division instead. Okay, have fun taking 10 times as long doing the problem then. All right, so once you factor it, this quotient might be factorable. If the quotient is factorable, go ahead and factor it. If it's not, if the degree is 3 or higher, you need to go back to this process of going through your possible rational zeros and finding one that works. So it's a go back up to here and try and find another one. But if you ever get a quotient that you know is factorable, it will always be quicker to factor than it will be to try and find a 0 that actually works. Now, if you get down to quadratic, you don't want to go up anymore. You just want to try and factor, and at that point, if it's not factorable, apply the quadratic formula. So when I say apply the formula, I mean apply the quadratic formula. There's a very important memo, and we will see this in an example, of course. I always make sure to handle these weirder issues. If you do have to go back to step 2, so if you keep having to do this synthetic division testing once you get a quotient. You don't have to test zeros that already failed. Once it fails, it always fails. But what that means is, let's say 2 did make the remainder 0. It could make it 0 again because it could have a multiplicity higher than 1. So there's an extra statement here you could say. If you have to repeat step 2, don't test zeros that already failed, comma, but do test zeros that have worked. You can also end up listing a new set of possible rational zeros for your quotient. You can list a whole new set of P's and Q's. Sometimes there will be less options doing that. And again, we'll go through all sorts of examples with this. I'm trying to find my examples, but let's not do all that yet. Let's start out with a slower approach. And let's just go up to this beginning stuff. I wanted to go ahead and lay out the instructions, but let's just work on finding the P's and the Q's and listing the PRZs. So let's go back up to just this stuff. I'm only going to focus on this part for now. In fact, I'll even slide it above these steps so we don't get confused. Example 1, and I can zoom in. List all possible rational zeros for f of x. Do not find zeros. So we're listing the possibilities. We're not going to find the ones that actually work. And this is something that a lot of students will goof up on. They'll go to the later problems where I say find the zeros, and they'll just list the PRZs. Follow instructions. So for A, we'll have f of x equals x to the 4th minus 3x squared plus 9x squared plus 2x plus 30. The important numbers in here are this 30 and the number that you don't see written in front of the x to the 4th, which is a 1. So I'll write it there just to emphasize. So we need to list the factors of these. It's kind of like the AC method. So we can go to the side. We'll list the factors of 1, which are just 1 times 1. And that gives us all the possible different values under Q, sorry. It doesn't really matter what you call them, P and Q. You can call them A and B, you can call them R and X, nobody cares. But the possible rational zeros are just the factors of the constant over the factors of the leading coefficient. Quite honestly, that's how I remember it. The factors of the constant over the factors of the leading coefficient. So there weren't a lot of options, but there are a lot of options for 30, splitting up the constant. You got 1 times 30, you got 2 times 15, you got 3 times 10, 4 times, nope, that doesn't work, 5 times 6. The next would be 6 times 5, which is a repeat, so I know I got all of them. And that makes up all the values of P, the 1, 2, 3, 5, 6, 10, 15, and 30. So our possible rational zeros are plus or minus. Now, in theory, you got to write this plus or minus on every single one of these. I'm just having this as a shortcut abbreviated version. So all the factors of the constant, we're going to have all the different factors of the constant, the 1, 2, 3, 5, 6, 10, 15, and 30. So 1, comma, 2, comma, 3, comma, 5, 6, 10, 15, and 30, all divided by the different factors of the leading coefficient. There was only a single factor of the leading coefficient. You don't want to repeat it, 1. But dividing by 1 does nothing. So the possible rational zeros are plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. So ignoring the plus or minus, that's 1, 2, 3, 4, 5, 6, 7, 8 different numbers. But because of the plus or minus, that is 16 different possible rational zeros. 16 that may work. Now, this polynomial is of degree 4. Remember, that's how many unique zeros you could have. So no more than 4 of these could work, and it's not even a guarantee that we have 4 unique ones that work. Maybe some of them are repeated. Maybe only 2 of these actually work at all. You could go through and test all 16 and maybe only 2 of them work. And you might go, well, what does that mean? Does that mean there's multiplicities? Maybe. But it could also mean that there are irrational zeros, things that have like a square root of 2 in them or an imaginary number in them. And that's something that a lot of students tend to pass over. They think that this lists all zeros, but no, it's all possible rational zeros, which means fractions. Let's do another one. Let's go back to black. Now, I am a bigger fan of testing on problems like this when you actually have to find which ones work. For listing possible rational zeros, I don't care. I'll do it like this too. 2x to the 7th, that looks like a 2, doesn't it? 2x to the 7th, undo, please. 2x to the 7th minus 3x to the 4th plus 8x minus 10. And again, the only numbers we really need to list the possible rational zeros are the leading coefficient and the constant. Make sure they're in descending order so you grab the right numbers, which they are. I am famous for putting these out of order, at least in one problem on a test. Hint, wink, nudge. I'm not guaranteeing it, I'm saying I like to do it. All right, so the factors of, let's do the constant first since I listed those first, because these are the numbers that go on top. So the P, again, that letter is arbitrary, is just us splitting up the 10, which is 1 times 10 or 2 times 5. The Q is us splitting up the 2, which is only one way to multiply to get 2. It's 1 times 2, using whole numbers. So now, because there's more than one option from the leading coefficient for its factors, that means we'll list all the P's, the 1, 2, 5, and 10, over the 1. Then we'll list the 1, 2, 5, and 10 over the 2. So your possible rational zeros would be plus or minus. So let's do everything over the 1 first. The 1, the 2, the 5, and the 10 over the 1. So 1, 2, and I'll go ahead and do these individually. I'll split them up, sorry. So 1 over 1, 2 over 1, 5 over 1, and 10 over 1. Again, the ones in the bottom were this one. The ones in the bottom were because there was a 1 in the Q. I haven't used the 2 at all. Comma. Now let's do the same 4 numbers in the top, the 1, the 2, the 5, and the 10 again, but now we'll do it over the other number from the Q list, the other number from the leading coefficient, the other factor. So that's 1 over 2, 2 over 2, 5 over 2, and 10 over 2. Well, obviously we don't need to write over the ones. So it's plus or minus 1, 2, 5, 10. The 1/2 is a half. We need to reduce some fractions. 2/2 is 1, then 5/2, and then 10/2 is 5. Notice something. This 1 and this 5 were already up here. You don't need to list them twice, just like we don't need to list multiple zeros twice. We just say, hey, they have multiplicity. So what we're going to do is just not write them. So plus or minus 1, 2, 5, 10, then a half, and 5/2. I do not care what the order of these are. I'm fairly confident that my math lab does not as well. If you find that it does, please let me know. But again, I'm fairly confident it doesn't matter the order. They don't need to be in some kind of ascending or descending order. So that is 1, 2, 3, 4, 5, 6 different numbers, but because of the plus or minus, that's 12 possible rational zeros. So I don't like problems like this one for the next set of examples because you've got fractions as possible rational zeros, which means you'd have to do the synthetic division with fractions. And especially in our compressed time, and the situation for our course, I just don't feel like it's necessary to do that. So I will give you problems where you have to list possible rational zeros and this leading coefficient is not necessarily a 1. But when I ask you to find the zeros, which will be the next set of examples, on a test, I will not give you a leading coefficient that isn't 1. In other words, when I ask you to find the zeros to go past what we've just done, you shouldn't see any fractions in here, which means you don't have to test fractions. If you get a homework problem that has it, I'll show you a way your calculator can help you sooner than later. Don't worry. All right. So that process for finding, we don't really need to see this. That was from before. That process for actually finding the zeros, now that we know how to list the possible rational zeros, let's actually go through it and find them without being told, hey, here's one that works, here's a hint. No hints. Use the possible rational zero to find all PRZs. That's what we just did in those last two examples. That's all we've done so far. We've only tackled step 1 in this section. Use synthetic division to find which one, actually find one that works. We've done synthetic division before, but not in this section. And I said a good method is to start with the smallest number in absolute, do its positive then negative, and work your way up until you find a remainder of 0. Factor, like we did in the very last example from last section. Then if your quotient's factorable, factor it. If you can do the quadratic formula on it, if it's quadratic, do that if you couldn't factor it. If it's cubic or higher, then you're gonna have to do this, you're gonna have to find another one that spits out a remainder of 0 by doing synthetic division. If you get a 0 that works, if you have to keep looping through, you might have to check it, you have to check it again because it might work again. It might not, it depends on the multiplicities. So I'm gonna try and leave these set of instructions up here for a little bit while we work on this first example. Ignore that, there we go. So example 2, one of the ultimate algebra problems, in my opinion. Find all zeros of the function for a. F of x equals x cubed plus 2x squared minus 5x minus 6. Oh, it's 4 terms, and we factor by grouping. And if it was factorable by grouping, go for it. But this one is not. So what we have to do is this brand new process. First thing we got to do is list the PRZs. So some side work. We need the factors of the leading coefficient, which is not seen, therefore it's a 1. And the factors of the constant, which is the negative 6. The sign doesn't matter for that. So to the side, the factors of the constant, which we're calling P, again, that letters are relevant. That's the 6. So that's 1 times 6 or 2 times 3. For the Q, the factors of the leading coefficient, which is a 1, it's only 1 times 1. Therefore, our possible rational zeros are plus or minus all the different factors of the constant divided by all the different factors of the leading coefficient. There's only one factor of the leading coefficient. It's a 1, so that means the denominators are 1, so we don't need to write. You don't have to write it. This will be the last time I do it before that. So it's 1 over 1, 2 over 1, 3 over 1, and 6 over 1. So just plus or minus 1, 2, 3, and 6. How many are there? There are 8 possible rational zeros. Now there are techniques. You can look at the sign pattern of the original function, how many times it changes signs, and use this thing called Descartes' rule of signs to eliminate certain zeros, the number of possible positive zeros, the number of possible negative zeros. Honestly, in most cases, it's more effort than it's worth. It's also not an official topic of this course. If this was a more advanced pre-calc, it would be. So I'm not going to get into it, but if you are studious, if you're going far in the world of math, then look into Descartes' rule of signs for eliminating some of these possible zeros. So out of these 8, you could try 6 first, you could try -3 first, you could try -2 first. It doesn't really matter. I said, with my problems, I like to start with the order of magnitude small and work my way up. So let's try +1. So I'm going to try +1. So that's the number that goes in the box. So I'm trying the possible rational 0 of 1. To the right of that go the coefficients of the function. This is us doing our synthetic division. So 1, 2, -5, -6, leave some space, plus sign, bring the first number down, and then it's multiply add. Make sure everything was in descending order, which I did. Make sure there's no zeros missing. We'll see one of those happen later. Multiply add. 1 times 1 is 1, 2 plus 1 is 3. 3 times 1 is 3, -5 plus 3 is -2. -2 times 1 is -2. -6 plus 2 is -8. So if we divided this function by x minus 1, because +1's in the box, that's us dividing the function by x minus 1. This would be the quotient and remainder. All I'm really interested in for the moment is the remainder, which is -8, and we said we want this to be 0. This is the number that helps us move forward. Well, guess what? -8 is not 0, so 1 fails. It fails now, it will fail for the rest of the problem. We never check +1 again. So now we try -1. It's kind of like factoring where you have to try some things and usually you end up wasting some time. The binomial that allows us to use synthetic division is that the denominator has to be x and then either plus or minus a number. So there cannot be a coefficient of the x, and there can't be any higher order terms like x squared or x cubed. So x minus 3, x plus 5, x minus 7, x plus a million, those are what the bottom can be, but it couldn't be 2x minus 5. But again, for all of this processing, every single one of those denominators is going to be x and then plus or minus a number by design. Thank you. All right, so back to this, the -1. To the right of it, we write the same 1, 2, -5, -6. There's going to be a lot of synthetic division today. We'll bring the 1 down, and then we multiply, add, multiply, add, multiply, add. So 1 times -1 is -1. 2 minus 1 is +1. 1 times -1 is -1. -5 plus -1 is -6. -6. Let me do that at the end of the problem. -6 times -1 is +6. And then -6 plus 6 is 0. And that is what we want to see. That is what we want to see. That tells us, because -1 being plugged into a synthetic division spits out a 0 remainder, that means that -1 is a 0. If so x equals -1 is a 0, means that x plus 1 is a factor. And that's what we really need. So this is going to drive us forward. So that tells us that our original function is divisible by x plus 1. If we divide this by x plus 1, you will get the quotient and the remainder seen with the 1, the 1, the -6, and the 0. So now we can rewrite our function. F of x is equal to, we write the factor, x plus 1. Remember, if minus 1 is the 0, plus 1 is the factor. If minus 1 is the 0, plus 1 is the factor. We were dividing by x plus 1. So then to the right of this goes the quotient. How do I get the quotient? It's based on the 1, and the -6. The -6 is the constant. The 1 is the coefficient of the x. And then this 1 is the coefficient of x squared. It's easiest to go from right to left. Remember that 0 was the remainder. So we just need the 1, and the -6. And I'll stick to red so you can see where everything came from. So that's 1x squared plus 1x minus 6. I know most of us probably don't feel the need to write those ones. I'm just being emphatic. So let me rewrite it without those. X squared plus x minus 6. So now we need to factor this guy or girl. If it's not factorable, we do the quadratic formula. If it was cubic or higher, we would continue on trying to find another 0 that spits a remainder of 0. But once it's quadratic, that's what it says up here. If the quotient is quadratic, then you want to factor or apply the formula. If it's cubic, maybe you can factor it, but it's rare. So we're trying to find a pair of numbers that multiplies to -6, but we'll subtract to 1. Well, that's 2 and 3. Let me just go over here. So that's x plus 1 still up front, times an x with a 2, and then an x with a 3. We got to make sure the difference comes out positive, so the 3 has to be positive and the 2 negative. That's the factored form of x squared plus x minus 6. It's x minus 2 times x plus 3. Now the goal of this problem was to find all zeros. We've found one of them thus far. We found the -1. We can find all of them. Well, now this is completely factored, so just set the function equal to 0. And Corey, I have not forgotten about you. I'm just waiting for the end of the problem. Sorry, let me do this again. So 0 equals x plus 1 times x minus 2 times x plus 3. And the first one's going to give us something we already know. X plus 1 equals 0 tells us x equals -1. X minus 2 equals 0, add 2 to both sides, you get x equals 2. Setting x plus 3 equal to 0, subtracting 3 on both sides gives us -3. Our 3 zeros, and we can very clearly see they all have a multiplicity of 1 because none of them have exponents. This was a cubic polynomial, so we have all the zeros. All right, so this is the note someone asked for a moment ago, a few moments ago. This is the this is the symbolic version of how you know whether you can do synthetic division or not. That the denominator, this is the emphasis right here. Oh, I don't want that. Wrong thing. There's no number in front of the x. There's no x squareds, there's no x cubes. It's just an x and then either adding or subtracting a constant. Any other form synthetic division will fail with. So I hope that helps. So I don't know. I think this is exciting. I really do. I'm a little geeky, I'm a little nerdy. I love that we now have the ability to pull zeros out of thin air with this almost seemingly random series of multiplications and additions, and then just use some basic concepts that we've seen before in order to ultimately get zeros, in order to ultimately factor something that was never factorable. So again, someone asked numerically, that's just f of x over, say, x plus 2, or f of x over x minus 17. If you had f of x over 2x minus 5, this you could not do synthetic division on because of that too. All right. B. I'm not going to be able to fit that there. So give me about 5 seconds for people to clear the writing, and then I'll scroll down. All right. Well, you're asking about a specific C. The C's are found using the possible rational zero test. So we had this polynomial, the x cubed plus 2x squared minus 5x minus 6. The way we know what the possible C's can be is based on We find all the different factors of the constant. We find all the different factors of the leading coefficient, and then we take the fraction of them. So the 1, 2, 3, and 6 either being positive or negative, those were our 8 different possibilities that would work. So we tried 1 and it failed. We tried -1 and it did not fail. It worked. So later down the line, we found 2 and -3 to be zeros. What that says is if we had tried +2 and if we had tried -3 using the synthetic division, those remainders would have been 0. They would have also given us a way to move forward. This is not the only way. I didn't have to start with -1. I could have started with +2. It would have given us a drastically different quotient. It would have given us a different thing to factor here, but it would have been factorable. And then we would have found the -1 and the -3. Now I'm gonna pull out the graphing calculator after one more example to show you a way to shortcut this, a way to know which ones will work and which ones won't work. But let's hold off on that. That'll be a really excellent tool. So for the function x cubed plus 7x squared plus 11x minus 3, we're still finding the zeros of this. It's not factorable via traditional methods. Maybe some method I'm not super reminiscent on. I can't tell you how many different factoring methods I've forgotten over the years because they're mostly useless. So first, we need a list of some possible numbers. So we need to list out the leading coefficient factors, the constant factors, and take the ratio of those two things in the proper order. So the P, again, this is the factors of the constant, which is 3. Well, it's just 1 times 3. It's the only option. The Q, this is the possible factors of the leading coefficient, which is 1. Well, that's just 1 times 1 again. I was mentioning earlier, in terms of testing, if I want the zeros, this is what I do. I'm not going to give you a 2x cubed or a 5x cubed or a 10x cubed. I'm going to avoid those fractions as possible rational zeros. So our possible rational zeros are plus or minus, because we don't know. It could be positive, it could be negative because of all the wonkiness. The factors of the constant divided by the factors of the leading coefficient. The factors of the constant are the 1 and the 3. And since the leading coefficient factors are only a 1, those denominators are 1s, which we don't need to write. So +1, -1, +3, and -3. There's only 4 possibles. Now again, I'm not saying there's only 4 possible solutions. I'm saying there's only 4 possible rational solutions. Fractions and whole numbers. There could be others that are involving square roots. There could be others involving imaginary numbers, which are inherently square roots, which is why they're called irrational. So let's find one that works. And again, I systematically generally go 1, -1, 3, -3. So let's try the 1 in the half box. To the right, these are in descending order in terms of powers. They're all accounted for. So 1, 7, 11, -3. Bring down the 1. 1 times 1 is 1. 7 plus 1 is 8. 8 times 1 is 8. 11 plus 8 is 19. 19 times 1 is 19. -3 plus 19 is 16. And that ain't 0, so 1 is trash. +1 is not a 0 now. It will not be a 0 in any other scenario of this function. So the next one I like to try is -1. So 1, 7, 11, -3. Leave some space, plus sign. Bring down the 1. 1 times -1 is -1. 7 plus -1, or 7 minus 1, is 6. 6 times -1 is -6. 11 minus 6 is 5. 5 times -1 is -5. -3 plus -5 is -8. And that is not the magic number of 0. So -1 is not a 0. It fails miserably. If we did this again on the quotient, it would still fail miserably. They're in the trash can permanently once they fail. If they work, you may have to try them again later. So +3. 1, 7, 11, -3. Plus sign. Bring the first one down. Multiply, add, multiply, add. 1 times 3 is 3. 7 plus 3 is 10. 10 times 3 is 30. 11 plus 30 is 41. Why did I feel like that's wrong? No, that's right. 41 times 3 is 123. Negative 3 plus 123 is 120. Definitely not 0. And it's cool that we now know these function outputs. F of 1 is 16. F of negative 1 is negative 8. F of 3 is 120. We could use those as points to help graph. Might be helpful if you were asked to graph, which you weren't. All right. So we had 4 possible zeros. 3 of them are in the trash. Cross your fingers, cross your fingers, cross your fingers and buckle up. Let me write that a little lower so it's not so squished. Negative 3. 1, 7, 11, negative 3. Line, plus sign. Bring the 1 down. 1 times negative 3 is negative 3. 7 minus 3 is 4. 7 times negative 3 is negative 12. 11 minus 12 is negative 1. Negative 1 times negative 3 is positive 3. Wipe the sweat off your forehead. Negative 3 plus 3 is 0. That's what we want. We finally found a 0 that works. As I said, it's kind of like factoring like trial and error. If there's 20 possibles, maybe you find it on the 20th possible one. So we found it on the last attempt. That's very frustrating if there's 20 possibles and we find our first one on the last attempt. Like I say, welcome to the real world. In terms of testing, traditionally, paper, pencil, I always make sure that if you're doing my recommended order of going in ascending absolutes, that you'll find it by the 3rd or 4th try at worst. So this is the remainder, which is 0, which tells us that the function f of negative 3 is 0. From right to left, and that's the quotient, that's the constant, the coefficient of x, and the coefficient of x squared. So the quotient is equal to 1x squared plus 4x minus 1. Again, if you need to see the 1, there it is. But what's important out of this is that since negative 3, via synthetic division, spit out a 0 remainder, x equals negative 3 is a 0, which also means that x plus 3 is a factor. So we can now rewrite our function. F of x can be rewritten as x plus 3, which if you set that equal to 0 would give you your negative 3 of a 0, times the quotient. It's always the factor times the quotient. And that quotient was the 1x squared, or just an x squared, plus 4x minus 1. So now, the x plus 3 we're done with. We just got to focus on this part, the x squared plus 4x minus 1. We ultimately got to find the zeros of that, which we could try this possible rational 0 stuff again. But this thing only has possible rational zeros of 1 and negative 1, which we already threw in the trash. So actually, no, we can't. All the synthetic divisions would fail on that. So instead, well, it's quadratic, so we try factoring it. But guess what? This guy right, I'm still on my highlighter. That second parentheses is prime. Give me a pair of numbers that multiplies to negative 1 or adds or subtracts to 4. You can only use 1 and 1, and the biggest number you can get there is 2, not 4. And since the subtraction is supposed to be 0. So that's prime in terms of rational numbers. So we got to use the quadratic formula. Good old friend. Negative b plus or minus the square root b squared minus 4ac all over 2a. Remember I said you never get to forget that? I don't lie. So for that particular problem, the a is 1, the b is 4, and the c is negative 1. Except for a little more space. So x equals negative 4 plus or minus square root, big square root, of b squared, which is 4 squared, minus 4, times a, which is 1, times c, which is negative 1, all over 2a, which is 2 times positive 1. So that's -4 plus or minus big square root. 16, is it minus or plus 4? Let's see. We got a -4 times a -1 at the end. So those two negatives cancel. It actually makes a +4. It's very common for people to make sign mistakes there. And in the bottom, 2 times 1 is 2. Let's go over here. So that's x equals -4 plus or minus the square root of 20 all over 2. Which is -4 plus or minus the square root of 20 you can write as 4 times 5. I'm writing the 4 in red for a reason because I know the square root of 4. It's 2. So that's -4 plus or minus 2 square root of 5 all over 2, leaving space for my red. And then we can reduce this. 2 goes into all of the outer factors. You can take a GCF out and then cancel, but I think a lot of us at this point just tend to do it this way. We cancel it everywhere. 2 goes into 4 twice, 2 goes into 2 once, and 2 goes into 2 once. If the denominator is 1, we don't need to write the denominator. So this is just -2 plus or minus square root of 5. That right there is 2 zeros. Let me not box that up. So that right there is 2 of the zeros because of the plus or minus. So one of them is -2 plus square root of 5, the other is -2 minus square root of 5. We found all of our zeros. We had -3, we got -2 plus square root of 5, and -2 minus square root of 5. So if I list them all at once, our zeros are x equals -3, and then -2 plus or minus square root of 5. Please use the plus or minus symbol appropriately in my math lab. I know some homework problems allow it, some don't. So make sure you figure out which ones do and don't. If it was a test question, if it doesn't give you credit, if you used a plus or minus, if you want it separated by commas, you can let me know and I'll give you full credit. Like I said, I'm okay giving partial credit on tests when it's something that has to do with notation or a typo, not when you have part of something right, but not the rest. And that's for these computer-based tests. If you notice that note earlier, I said there may be a small portion of the Chapter 3 test where you actually need to show me handwritten work and submit it via Canvas. That I would do my normal partial credit on because it would be a little more traditional. I'm actually looking at your work. How are we doing on time? 12 minutes. Okay, so let's now back up for a second. I mentioned calculator earlier. How can a calculator help us? If I have 20 possible rational zeros, I don't want to find my first one on the 20th attempt. That would suck, right? Calculators are helpful for alleviating that pain. So let's go back up to example 2a, where we found the zeros were -1, 2, and -3. We tried +1 as a possibility. It failed. We got -1 and it worked. So out of those 8 options, 3 of them would work. Let's look at this one though. B. There were 4 options. The first 3 failed. The 4th one worked. The other 2 zeros were irrational because of the square root. You can't find these 2 zeros by doing the possible rational zero test, the rational zero theorem. You can't find these. You have to find these algebraically. So don't expect all of the possible rational zeros to be zeros. It's very common that there are only some of them. So let's pull out our calculator. Let's turn it on. Let's go to the graph screen and let's show you how you can kind of alleviate testing 4 or 5 or 10 possible zeros and go straight to one that works. So let's go to the y equals x to the 3rd plus 2x squared minus 5x minus 6. Let's make sure I type that right. X cubed plus 2x squared minus 5x minus 6. And let's go to graph. So here's the graph of this polynomial, something we would have been capable of graphing a couple of sections ago now that we know how to find zeros. So I could actually take this topic, throw it into the topic a couple sections ago, because a couple sections ago we said all the problems would be factorable in order to graph them. Now they don't have to be because we have an extended method of finding zeros. So I could ask you to graph this function. I won't, because that's a whole lot of work. The work to find the zeros is a problem by itself, then to graph it is another problem. Now what I could do is make it a two-parter, but I generally don't. Okay, what's the point I'm trying to get at? The possible zeros we found were plus or minus 1, 2, 3, and 6, 8 possibilities. Looking at this, I can see 3 of them. Remember, what does it mean to be a zero? It means that it's an x-intercept. It's where we cross the x-axis. I hope you can see my mouse. I'm sure you can. We're crossing right here, then right here, and then right here. There are my 3 zeros for this function, the 3 rational real zeros at least. Oh, well, and I don't even know that they're rational. Let me just say the 3 real zeros. It looks like they're going through at nice numbers. Let me hit my trace button and just kind of move around over here. Okay, well, I can't really just move this up to a 2, but once I hit trace, if I type 2 and then hit enter, it will tell me exactly what that output is. And look at this. At x equals 2, the output is 0, so that says 2 is a 0. Look here, our algebra confirmed that. X equals 2 was a 0. So your calculator just gives you the answer. If you trace back over to here, all right, we're crossing the y-axis around what feels like -1. Maybe if I type -1, look at that, y equals 0. Look at +1. If I type 1 and hit enter, the y value is -8. That's how you skip doing synthetic division on +1. So you list your possible rational zeros, 1, 2, 3, and 6, positive, negative. If I just go to the graph, hit trace, type 1, and hit enter, I can see it's not crossing the axis at 1, so it's going to fail it. And look at that, it even spits out -8. The output is the remainder. But if I then type -1, look at that, remainder is 0. So I know -1 works. If I try +2, 0. So I could then do my synthetic division and get the quotient with 2. What if I tried -2? Nope, that's not 0. So -2 would fail the synthetic division. What if I tried +3? Nope, it fails it. What if I try -3? It works. What if I tried +6? It fails. What if I try -6? It works. Now you don't have to try all 8. You just got to put your eyes on one that works and then do the synthetic division with the one that works. So let's try this visual aid out with B. So we failed synthetic division 3 times. It felt like a waste of time. Let's see how the technology could have helped us. And again, I don't like technology for you doing arithmetic. I don't like technology as a crutch. I like technology to help you with big picture ideas, and this is a big picture idea, to save you time when there's crazier things going on. So x cubed plus 7x squared plus 11x minus 3. Let's go to the graph. All right, so I can see 3 zeros. So I can see 3 real zeros. They're here, here, and about here. And if I hit, I know my possible rational zeros. We can list those. You still need to list those, plus or minus 1 and plus or minus 3. If I hit trace, and then I type 1, spits out 16. Nope, that doesn't work. Ooh, look, the remainder is 16. The remainder theorem is awesome. It's true. So 1 fails, don't do the synthetic division. All right, maybe -1 works. Nope, fails, skip the synthetic division. All right, well, maybe +3 works. Nope, fails, skip the synthetic division. Maybe -3 works. The remainder, or the output 0, which means the remainder is 0. Boom, we got one that works. Now, you don't have to go typing it in. You could say, oh, I think this is at -3. You can skip the 1s and -1s. You can visually see, no, it's not crossing at 1 and -1. It's crossing somewhere between 0 and 1, though. So you can actually get this -3, but if I try and figure out where this one over here is, -4.25, and that's negative, -4.04, maybe it's like -4.1. That's close, but it's a little too high, so maybe it's -4.2. Nope, maybe it's -4.25. You can see that this is going to get tedious when they're not whole numbers. And that's because you literally can't figure this out this way because those solutions were irrational. The same thing for this one over here. If you go to trace at, like, say 0.1, maybe, that's negative. Let's try 0.2, still negative, 0.3, positive. So it's somewhere between 0.2 and 0.3, but you're not going to be able to zero in, pun intended, on that value. But you're always given at least one rational zero for these problems. Otherwise, we wouldn't know how to begin this. It's a much more complicated problem that is not pre-calc level. So again, this technology can really help you narrow down which ones to try and which ones not to try, especially in the case where there's 20 plus possible rational zeros. If you've got 20 zeros and you go, let me get my TI-83 so I can see which one works and skip failing on 19 or 15 or even 10 of them. So this is awesome use of technology. I love it. I hope that you understand how we were using it and that you might be able to skip some synthetic divisions that would fail. All right, still not ready for that note. C, can we fit it here? I'm gonna try. So f of x is equal to x cubed minus 4x squared plus 8x minus 5. I think I just saw a question. Did. The square roots are rational. When you have a square root in a solution, because you can't take the square root, that makes it irrational, irrational. Rational zeros do not have square roots in them. So rational zeros are like +3, -7/2, 41, 3.7. So again, rational means whole numbers and fractions. Irrational means it has a square root or an I in the answer somewhere. All right, how are we on time? Oh, you know what? We only have like 5 minutes left. We are not going to be able to finish this problem in that amount of time. So since I went a couple minutes over last time, I'll go a couple minutes under this time. But you know what we're going to start with on C. Honestly, try this at home. Let's use our technology real quick to push us in the right direction. I'll still, if I need to do extra synthetic division next time, I will. But let's see. So x to the third minus 4x squared plus 8x minus 5. Do I have everything right? X cubed minus 4x squared plus 8x minus 5. Good. Let's go to graph it. Now, this one is fun. The last two problems we had were cubic, and we saw that there were 3 zeros. This only crosses the x-axis once, which means there's only one real zero. Now, maybe it has a multiplicity of 3. It'd be weird, but maybe that's the case. Or maybe it's got a single real zero, and it's got 2 imaginary zeros. That's another possibility. Can we hone in on this zero with our graph to skip the, excuse me, the failing of a bunch of synthetic divisions? Let's try it. Trace. What number does that look like it is? If all these marks are 1, it looks like it's 1. And yeah, the y value gets pretty close to 0 right around 1. So let me type 1 and hit enter. And sure enough, the y value is 0, which means +1 is a 0, which means -1 is the factor. So next class, I'll show the synthetic division for good measure that +1 does work, but every other possible rational zero, which are going to be -1, +5, and -5, spoiler alerts, those would fail. It's not crossing at -5, it's not crossing at +5, it's not crossing at -1. So hopefully the other 2 zeros will be able to be found. We'll probably need the quadratic formula. And on that note, we'll call it a day, having finished 3.3 and done a decent chunk out of 3.4. Chapter 3 homework due dates will be the day before Chapter 3 test is due. Chapter 4 homework due dates will be the day of the final exam. I know I have no due dates up there yet. The Chapter 3 ones will go in soon. I'm still working out the kinks with the final exam. Like I said, it's probably going to be Thursday, that May 7th. I'm fairly confident it's our last day. And like I said, that'll be a 24-hour exam with a time limit that we'll have more details on later. Of course, you'll get a review. But for now, have a good day, have a good afternoon. It's a little warm, maybe you can get outside. And we'll see you next time.